questions? Okay, so today, we covered one well-known and important algorithm in machine learning or artificial intelligence, and now today we're going to begin to tackle maybe the most well-known artificial learning or machine learning algorithm or method, and that's probably you've heard the word. That's pretty well known. It's called neural network. So we're going to be talking about neural networks today and next week. And for online resources, in case you're interested, I've put a bunch of them here, and they are specifically here. So this one is one of my favorite, Khan Academy, and he does linear algebra there, and he does a very good job. He does a very good job with everything, and he definitely does a good job here. It's pretty long. It's a whole course, really, on linear algebra. But if you want to end up doing this kind of work, you're going to have to know linear algebra. So this is one way to learn linear algebra. And then also, here's an, yeah. Sorry, will we need linear algebra? No, definitely not. It's too much. I mean, you'd have to have studied it a lot to do it, and we couldn't do it here. It takes a long time to do it, but it's very good. Sorry, no. Linear algebra? No, neural networks. Oh yeah, you'll see that. We're going to do that. Yes. Okay, now this is a very good lecture on neural networks. Now you may not understand it until after we finish, but after we finish, hopefully you will understand this. And this comes from this course here at MIT called Artificial Intelligence, and it's very good, and there's many lectures there. So, but the neural network one is very good, and you can check that out. I'll give you the PowerPoint. Now this is much harder. This one is by somebody named Hugo La Rochelle, and he's in Canada. And there's some very good research coming out of not his university, but apparently he was a student of a different university. I forget where it is, but it's in Montreal. And there's very good research coming out of those guys. There's a guy here in Montreal, rather, and somebody at NYU who's French, but he's at NYU. And they're doing stuff with image recognition and computer vision. They call it computer vision. And they're using neural networks, and very good work that they're doing. And this guy, Hugo La Rochelle, I guess he was a grad student recently, and now he has a position here at this school. And he has a very good course here on neural networks, but it's not simple at all. And it definitely requires linear algebra. Okay, so you have to do linear algebra first before you do that, but it's very good. This is a great book, online book on neural networks, and I forget. I think he assumes there's some linear algebra, not much. This is much easier than the other one, than the previous one, but very good also. In fact, a lot of our lecture today is going to come from this. This one I don't know what that is. And then, as I said here, the linear algebra. Okay, so you can check these out. I'll give you this PowerPoint. Now, in order to do neural networks properly, you have to have studied some calculus. So how many people have studied something like this. So how many people have studied, let's see, this symbol here? Just this part here. How many people have studied this symbol? No? Nobody's ever studied it? It's a derivative, right? Differentiation. Is there anybody in the room who hasn't studied it? So you're all familiar with it. Okay, that's great. Okay, then this can be kind of a review of that. So we're going to need that. So I'll come back to that in a second. And we're also going to need, so that has to do with derivatives, partial derivatives, and gradients. Now actually, for our discussion, we don't need partial derivatives or gradients because that comes into play if you're talking about more than one variable. And I'm going to keep it simple and just one variable because when you get into more than one variable, then that's when you start to need linear algebra. So I'm going to keep it simple and avoid that. But just to let you know, in order to, I'm kind of giving you this in a funny way. I'm kind of like trying to weave my way through and present certain stuff to you clearly, like not water it down at all. But I'm sort of finding my way through and only picking out the parts that we actually need. But if you want to continue to study, you really need the whole breadth of the topic, like linear algebra and so on. So, just to warn you, just to let you know that that's the way you have to go ahead. How about the dot product? How many people are familiar with the so-called dot product in vectors, right? So let me just quickly review that. Has anybody not seen dot product before? Okay, you haven't. So it's nothing really. Just a notation, really. That's all it is. Just a notation. So, in other words, suppose we have a list like this, a list of numbers here, and another list of numbers here. We can talk about multiplying these two lists. Now, usually we call these vectors. So we have a vector here and a vector here, but you don't have to call it a vector. It's called a list. And you can multiply these two. Now, what could we mean by multiplying these two? So really, there's no necessary meaning that we have to give to it because it's just, we could mean anything, lots of different things. We could choose to mean what we mean. Because multiplication really refers to multiplying two numbers, right? Not multiplying two lists. So we can give it we can give whatever meaning we want. So you might say, okay, am I going to mean this? So what did I do here? What did I do in this top row? What did I mean by multiplying? Here's the multiplying operator here. So what did I do in this one? I took 1 times 5, put it here. I took 2 times 6, I put it here, and so on, right? Okay, so then maybe that's what I mean, or maybe that's what I want to mean. Or here's an alternative meaning, or an alternative definition. What's this one? I took 1 times 5, put it here, then I put a plus 2 times 6 plus 3 times 7 plus 4 times 8, okay? Everyone see these are two different results? Okay? This is the big difference between these two is that the result here is not a number, it's a vector, or a list, if you want to call it a list. But the second one, the result is what? A scalar, right? A number. Okay? So there's no right answer to what we could do for this, but what they generally mean by this dot is this one. Okay? So it refers to taking the first one from here times the first one from here, plus the second one from here times the second one, and so on. Okay? So this would be, what would it actually be? 5 plus 12 plus 21 plus 32 is what? Anybody quick? 12 is 17, plus 21 is 38, plus 32 is 70. Okay, so this would be 7. Okay, so anyway, that's a number, right? It's not a list. It's not a vector. Okay? So that's what's generally meant by the dot product. And here, this comes from Wikipedia. It's exactly the same thing. So suppose you have A is this list or this vector, and B is this vector. And what do you mean by A times B? You mean this. Okay, does everybody see? Everyone understand? So it's just a notation. Okay, it's just a notation. In other words, let me put it this way. Instead of having to write this long thing, sometimes we might just write this, A times B. Okay, it just makes it shorter, that's all. It doesn't do nothing but that. Okay? Is this clear? Everybody get it? Okay, maybe I should have made this bigger. Like that. Okay? Alright, so that's called the dot product. And here's something else we're going to need, called the sigmoid curve, which is just a curve. It's just you can obviously see that it's a curve, right? And this just turns out to be an important or useful curve. And so, first of all, most curves that we deal with have equations, right? So this curve has an equation. And the equation for this one is here. Okay, so everybody's familiar with E, right? Okay, can I ask that you stop surfing the net and pay attention? So everybody's familiar with, okay, like stop, take your hand off the mouse and try and let go of the mouse. I know it's addictive, but just try and take your hand off. Can you take your hand off the mouse? Everybody's familiar with E, right? So this is yes? Yeah. So this is a function that involves E, right? The variable here is what? T. And so we put in T in here, we calculate this part, we add 1 to it, we flip it over, and that's this curve. Okay, so it's not so terribly complicated. And the shape of this curve turns out to have this shape. So the important things to notice here are, first of all, what they mean is that it never goes higher than 1. Can you pick that up by this picture? That's what they're trying to draw here. Is that it doesn't go beyond 1, and it doesn't go below what? 0. Okay, so it goes from there to there. And what's the shape of it? Anybody? What? It's an S, right? It looks kind of like an S, so they call it sigmoid curve. Okay? But it's also called a logistic function. What? Yes, sometimes I think they use it, yeah. They use it for lots of different things, just because, not because it represents reality in the real world, but because it's convenient. That's all. Okay, like, I heard another professor here telling me that there are some people who think like this is every natural phenomenon in the world follows this curve, which is just like crazy. I don't know. Like, to believe something like that, personally, I would never believe it. But anyway, people are kind of in love with this curve. That's what I guess I can say. But I'm not in love with it. But it's convenient. Okay? So, anyway, we're going to need it. We're going to use it, rather. I don't know if we need it, but we're going to use it. Okay, and the reason we're going to use it is because when the guys that were trying to figure out how to design a neural network were thinking about it, they thought, well, let's use this because it's easy. And it's easy because of certain things. It's easy because if you take the derivative of it, it turns out to be very kind of nice. So that's not apparent right now, but it is true. Okay, so that's why they use it, not because it represents reality, but just because it was easy. Okay? So there are certain things about the sigmoid function that we can mention. First of all, it's continuous. Does everyone agree that it's continuous? Yeah, it's smooth, right? It doesn't jump up somewhere and stuff like that. So it's continuous. And so much easier to work with mathematically than a different function, which we're going to see, a step function. You know what a step function is? Yeah, it jumps up. Right, so that's not so easy to deal with mathematically because it's not continuous, because it jumps. That makes it hard to deal with. Secondly, as x goes to infinity, y goes to 1. That's what we said here, right? As it never gets higher than 1, but it's approaching 1. Okay? So as x goes to infinity, it gets closer and closer to 1. So that's another reason that it's convenient. It's not clear why that would be good, but it will turn out to be good. Another thing is, number 3, better yet, the derivative of the sigmoid function is really convenient. That's the part I was going to say. If y equals this, the derivative turns out to look like that, which is very, like the derivative is just a function of y. That's a kind of very unusual thing. You don't usually get that, and maybe you don't remember much about derivatives. But anyway, trust me, it doesn't happen. Okay, so this is very simple and nice, and that's attractive. Okay, so it turns out to be useful. Okay, now I do want to review this concept about the derivative. Okay, so first of all, you probably, since you studied derivatives, if I asked you, what's the derivative? I'm going to write this on the board because I didn't put it on the screen, but what's the derivative of, suppose f of x equals x squared, and I say, what's the derivative of f of x? That means, what's the derivative of x squared, right? Does everybody remember that one? It's 2x, right? Right? 2x. So do you remember that? So what is the derivative telling us in general about a curve? The slope, right? The rate of change of the curve, right? The slope. Right? Tells us the slope of the curve. So this means that the curve was like that. So if I want to know what's the slope here of that line, the derivative will tell me that. Okay? But a little bit more literally, it's asking, when I write d of f of x over dx, I'm saying, how does f of x change when I change x, right? Isn't that what it means? How does f of x change when I change x, right? When I change x by a little bit, how does the height change? That's basically the slope, right? Right? Okay? So it means, how does f of x change when I change x? Does everyone see that? Okay? That's basically what the derivative is. And for our purposes, that's what we wanted. That's the point of view that we want to think about it from. Now, I go back to this screen here. But this one is different. And you should notice the difference here. What did I say over here? Look at this one versus that one. Obviously, it's not the same. What is the difference? Literally, it's different. What is the literal difference between the one there and the one I have on the board? What? Yeah, the literal difference is u. Now, generally, it doesn't matter. If you use a different letter for things, it doesn't make any difference, right? But that's not the point. The point is that this x and this x are the same, right? But not in here. So if I had this and I had a du there at the bottom, then it would just be a different symbol and we wouldn't care, right? A different letter and we wouldn't care. But that's not the situation here. Okay? Do you agree? This is not the same variable as this, right? Did everyone see that? This is the same variable as this. So you learned this rule doesn't mean you can use it here. Okay? You understand? You learned this rule, it does not mean you can use it here. Okay? So what this is let's see. Where's the start of this? Okay. So here's the function h. Now, H is made up kind of two parts. So this is one part of it now. I can't do it. This is one part of it, and then we're going to raise this thing to this power. Okay, do you understand? So I'm going to call the inside part u of x, because it is a function of x, right? Don't you agree? It is a function of x, so I can call it something of x. I'll call it u of x. Okay, so then I'm going to call the other part, now there's another part which is raising something to the fifth power. Okay, so I can say that I took u, or u of x if you want to write it fully, and raised it to the fifth power, I'm sorry, to the half power, to the 0.5 power, right? Okay, so I can say that there's a function raising stuff to the 0.5 power, and there's another function which is 3 times something plus 1. Okay, so I'm putting one function into the other. Okay, and that's referred to as function composition, composing two functions. Okay? All right, does everyone understand that? Now, if you look at this, just here, if I ignore the x here, I could say, what's the derivative of f with respect to u? That means if I change u, how does f change? Right? Does everyone understand that? That would be, well, I don't have it written down, but that would be like this. That would be this. df du. Okay, that would be df du. But I could ask a different question, and I want you to decide whether it makes sense to ask the question. Not what the answer is, just whether it makes sense to ask what the question is. And it's not the same as this question. This question. df dx. So what that means is, if I change x, does f change? So we already agreed that if I change u, f will change, right? Because f is a function of u. Now I'm asking a different question. What am I asking? If I change x, will f change? And what's the answer? Yes, it will. Why? Because when I change x, u will change. And if u change, right? Because where did I put it now? Where is it? Where did I have it? Here. Because f, when I change x, what's going to happen? U will change, because what's u? This part is u, right? So u is a function of x, so if I change x, u will change, right? But if u changes, we already said that what? F will change, right? Does everyone see what I'm talking about? And that's called the chain rule. And why is it called the chain rule? Because when you change one thing, it causes one part to change, but when you cause that part to change, it causes the next part to change, right? Okay? And this is called the chain rule. And the question is, now you understand that this question is different than this question, right? Right? Now you understand that. Now the question is, what's the formula for this one? Okay, that's the question we need. That's the formula we need for our work in neural networks. Okay, so I don't know if you studied it or not. The answer is called the chain rule, and it looks like let's find it. It looks like, where is it? No. Don't think it's a nice one. No. All right, let's look it up on the internet. always a good alternative. Unless they have it here. Okay. Looks like, I thought they must have it here somewhere, but it's probably faster just to look it up on the internet. So here's the answer, probably. Yeah, I hope it's not a complicated one. Otherwise, we'll look at the images. Okay, here's the answer. Okay? So here's the situation. They're using just a little different notation. But what we have is that z, in our last example, we had what? F was a function of u, and u was a function of x, right? Right? F was a function of u, and u was a function of x, right? Now they're calling f z. Okay, so it's a different presentation, so they're using different variables. Okay, so they're saying dz dx, right, is what? So here, let me write it here. So what they're saying is here, z is a function of y, but y is a function, I guess a different function, of x. Okay, you understand? So it's the same thing. When we change this, y changes, and when we change y, f changes, so z changes. Right? Okay? So our question is this. We know that this question makes sense, but that's not the question we want to ask. We know that when we change y, we can ask how does z change, but we want to ask when we change x, how does z change? Okay? And the answer is going to be like this. Now, you have to prove this answer. It's not just like, because it looks right. You have to prove it. But the answer turns out to be that it's dz dy times dy dx. Now, that looks like you're canceling, and it works out perfectly. But when derivatives, you can't cancel like that. These symbols this isn't a piece and this isn't a piece. It looks like they're pieces, but they're not. Okay? So you can't, it's not really canceling, but it looks like it anyway. But anyway, the answer is what? We said that z depends on y, right? Right? So it makes sense to ask this. The derivative of z with respect to y. Right? Makes sense to ask that. And we said that y depends on x. So it makes sense to ask dy dx. Right? Okay, so both of these make sense. And so the answer to this one is the product of these two. And that's called the chain rule. Okay? Now if you had a kind of longer, like z was a function of y was a function of x, and x was a function of something else, you could make a longer chain rule. And we might need something like that in our neural network. But the basic idea is this. Okay? So we're asking, when we change x, how does z change? But z is not directly a function of x. It's a function of y, but y is a function of x. That's called the chain rule. Okay? So we need that. We'll need that. Not probably today, but we'll need it. Okay? And, okay, so I guess I don't need this anymore. Okay, so this symbol just means this, and this symbol means that x goes into g, but then g goes into f. Okay? And our question would be, what is dz dx? And we just answered that. Okay? This is just another notation for this. Okay. Any questions about that? Okay, now this is what we just did. What is this again? This is called what? Dot product. That's just a notational convenience. So instead of writing this, we can write this. Instead of writing this, we can write this. Okay? So, nothing there. And this is the sigmoid curve, which we just mentioned some properties of it here. Okay, now let's introduce one typical problem that a neural network might try to solve. Now, neural networks are used for everything, not just this typical problem, not just this problem. Like, people are using it to forecast stock market, people are using it to do all kinds of things, to drive cars, and all kinds of stuff, right? So this is just one problem as an example, just to give us something to focus on. Okay, so if you see these handwritten digits here, most people would effortlessly recognize those digits as 504192. Okay? Recognizing handwritten digits isn't easy, though, but it's just that humans are amazingly good at making sense of what our eyes show us. Okay, so it's not that it's easy, it's just that we have very powerful neural networks in our brain. All that work is done unconsciously, and so we don't usually appreciate how tough a problem our visual systems solve. However, neural networks approach the problem in a different way. So if we want a computer to try and do this, you have to figure out something that might allow them to do it. So the idea is to take a large number of handwritten digits known as training examples. And we used that word a little bit before. So we'd have all these handwritten digits, and like if I ask you what this is, of course you know what it is. If I ask you what this is, of course you know what it is. And we would tell the computer, oh, this one is a 7. This one is a 3. This one is a 2. So we tell it what the handwritten digits are. Okay? And based on that, it's supposed to learn to recognize future handwritten digits. Okay, do you get it? And that's called a training set in machine learning. Yes? With what? Oh, yes, it's exactly that. Yes. Yes, it's exactly that. And also, like I think, well, a variation of this is a little different. You know when you take your phone and you point it at your iPhone, I think iPhone has it, and it recognizes this is a face, right? Whereas this over here is not a face, right? That's a variation of this called a convolutional neural network. I mean, it's a neural network. Just people have tried to get them to be able to recognize that there's a face there as opposed to a cow, or as opposed to a turkey, or something else, right? Or a flower, or whatever. So that's a type of neural network. So these are known as the training examples, and then we develop a system which can learn from those training examples. In other words, the neural network uses the examples to automatically infer rules for recognizing handwritten digits. Furthermore, by increasing the number of training examples, so if we get more training examples, the network can learn more about handwriting, and so it can improve its accuracy. So while we've just shown 100 training digits here, 10 by 10, we could build a better handwriting one by using more digits, or more training examples. Okay? So we're focusing on handwriting recognition because it's a good example, a prototype problem for learning about neural networks in general, but it's definitely just one of a million different examples. Okay? Okay, so first we talk about what are called perceptrons, and that's a type of artificial neuron, and it's called a perceptron, and these were developed in the 1950s and 1960s by the scientist Frank Rosenblatt, inspired by earlier work by Warren McCullough and Walter Pitts. A perceptron takes, so here we're going to start our discussion of neural networks. We're going to start out with the discussion of a perceptron. So a perceptron takes several binary inputs, x1, x2, pardon me, but I didn't use subscripts here. This should be x of 1, this should be x of 2, and so on, but it's really a lot of trouble to do that, to make a subscript so much trouble in Word or PowerPoint or something like that, so I didn't do it. And produces a, so it really should look like that, x1, x2, x3, and produces a single binary output. So in other words, we're going to take the different inputs, x1, x2, and so on. We're going to put them, we're going to send them into like what we call a neuron, and that's going to output something based on what these are. Okay, and let's call it perceptron. And these should be binary inputs. What does binary mean? What? 0, 1 inputs, right. So for now, we just have binary inputs. In the example shown, the perceptron has 3 inputs. In general, it could have more or fewer inputs. Rosenblatt proposed a simple rule to compute the output. He introduced weights, W1, W2, so again, these should be subscripts, okay, which are real numbers expressing the importance of the respective inputs to the output. So do you understand? We're going to put a weight here, a weight here, a weight here, a weight like a number. Okay, so maybe this is 3, 4, and 5. So if I put 3, 4, and 5, which input is the most important? According to the way I've put the weights. If I put 3 as a weight for this, what I mean by a weight is I'm going to take this, whatever this is, and multiply it by 3. Whatever this is, I'm going to multiply it by 4. And whatever this is, I'm going to multiply by 5. And then I'm going to add those, all 3 of those results to get here. So if I did that, which one am I saying is the most important input? The last one, right? Because I'm weighting it by 5. Whereas the other ones I'm weighting by 2 and 3, right? Okay, so that's what we mean by weights. Okay, so the neuron's output is going to be either 0 or 1. That's another thing that we're going to require. The output is going to be either 0 or 1. So first of all, we're going to do this calculation like I just said. Now remember, these are binary, right? We said these are going to be binary. Then we're going to put some weights here, so we're going to take some binary times this weight, plus some binary times this weight, plus some binary times this weight. And you can see where the dot product is coming in, maybe. But anyway, even if you don't. Okay, so we're going to do that. We're going to add them up, and that's going to go into here. And then we're going to have some way to calculate from that number what the output is. Okay? And the output is only, for this, is only going to be 0 or 1 for our so-called perceptron. This is a very, very basic kind of scenario, which he only did a long time ago in the 1950s. Now they've come up with a lot more. So the neuron's output, 0 or 1, is determined by whether the weighted sum, now pardon me again, but I didn't use subscripts here, but I mean to say W sub j and X sub j. So W sub j stands for what? W sub 1, W sub 2, W sub 3 are the weights. And we're going to take x1 times W1 plus x2 times W2 plus x3 times W3, and we're going to sum them up. That's what this means, right? Okay? So the neuron's output, 0 or 1, is determined by whether the weighted sum is less than or greater than some threshold value. So we're going to set some threshold value here, and if this is greater than that value, we'll output a 1, and if this is less than that value, we're going to output a 0. Okay? So let's see if maybe we'll have an example that makes it a little clearer. But do you understand what I'm saying? So again, we're going to take values, multiply them times w's, add them up, we're going to get something here. If it's greater than something, we're going to decide the something, the threshold value. Then we'll output a 1, and otherwise we'll output a 0. Okay? And this is supposed to model in a very simple way the way the brain works. Because the brain has these little neurons, and sometimes they fire, and sometimes they don't. So if there's enough energy sent into the neuron, it will fire. And if there's not enough, it'll just sit there. Okay? So this is supposed to model that process. That's where they got the idea. That's why it's called a neural network. Okay? Does everyone follow so far? Okay, to put it in more precise algebraic terms, so the output is going to be what? Either 0 or 1. And it's going to be determined by what? If the input, okay, now does that, first of all, get used to this. Does everyone recognize this as the input? Okay, this is the input. So if this input is less than the threshold, it'll be 0, and if it's greater than the threshold, it will be 1. Okay? And that's all there is to how a perceptron works. That's it. Okay, that's a perceptron. We're going to amplify that or expand that idea a little bit more to get to a neural network, but this is a basic idea anyway. Okay, so everyone follow this? Okay, guys, quit chatting and pay attention. Okay, so here's a perceptron, like we just said. So of course you can change the weights to get different outputs. So if I change these weights, I'll get some different responses, right? Okay? And also you can add more perceptrons to the network. So now we have more. So what we're saying here is these are the inputs over here. So this would be x1, x2, x3, x4, x5. Okay? And then we're going to take x1 and we're going to multiply it times weight, weight, weight. Wrong. I said it wrong. That's wrong. Wrong. We're going to take x. What's going to go into this? I said it wrong. I mean, I was right, but not that obscures the point. What's going to go into here? x1 times this weight, x2 times this weight, x3 times this weight, and so on. Then I can say what's going to go into here, and similarly, right? Okay? Everyone follow this? And then, once I get something here, here, and here, what can I do? This is going to have an output. So I can say, what's going to come into here? I'm going to take the output from here and multiply times this weight, plus the output from here and multiply times this weight, plus the output from here and multiply, right? So we can line these up, right? And so we could make a very complicated system. And that would kind of model a very complicated decision process, or that could model or represent a very complicated decision process. Okay? Any questions? So before we said that a perceptron has just a single output, but it looks like this one here has more than one output, right? But actually these are the same. The output goes here, goes here, goes here, goes here, but it's the same value. Okay, so it looks like it has different outputs, but actually there's only one thing coming out. It just goes to different places. Okay? In the network above, the perceptrons look like they have multiple outputs. In fact, they're still single output. The multiple output arrows are merely a useful way of indicating that the output from a perceptron is being used as input to several other perceptrons. Okay? So it's just a small point, but could be confusing. Any questions so far? Okay, now we're going to try and simplify this, or change it, rewrite it in a different way. Let's simplify the way we describe perceptrons. So we just said that the condition that the input is greater than some threshold value. If it's greater than the threshold value, then what do we output? Let's see if you're following me. if this is greater than the threshold value, what do we output? 1. And if it's less than this value, threshold value, what do we output? 0. Okay, so you are following. Okay. Anyway, this they suggest is a little bit cumbersome, so we can make 2 notational changes to simplify it. First, instead of this, we can use the dot product, right? So we already said that we could that might be convenient, right? So this is w sub j x sub j, right? So that can be changed to the dot product. In other words, this. Again, I apologize. No subscripts here, but right? Sigma w sub j x sub j could be written as w dot x, right? Okay, so we don't have to write this, we can write this. All right? Hopefully that's not just a notation. So, where w and x are vectors whose components are the weights and inputs respectively. So let's just be clear. What is w here? This is a vector of the weights, right? So what were, I gave you a sample of weights here. What were the sample weights I told you? 2, 3, 4, I'm sorry. What did I say? 3, 4, 5. So W1 would be 3, W2 would be 4, and W3 would be 5, right? Okay, so it would be 3, 4, 5. So that would be the vector W. And then the inputs, we didn't give any sample, but we'd have a vector of inputs as well, right? Okay. And secondly, okay, so first we can do this. So we'll write w dot x to mean this. But recall that w and x are vectors here. They're lists, right? Okay, now the second change is to move the threshold to the other side of the inequality and to replace it by what's known as the perceptron's bias. So the bias is just the negative of the threshold. So in other words, first of all, this is w dot x. We already dealt with that part, right? W dot x. But before we had b over here, before we had the threshold over here, we're calling the threshold minus, we're calling b minus the threshold. So if we bring it over to here, it becomes plus. Okay? So b is minus the threshold, so if I bring it over here, it becomes plus. Okay, so I don't know, it seems more complicated to do this, but that's what they're doing, and it's not too much more complicated. Okay, so now we have this picture, this set formula. It's really the same thing. Notice when the bias is large and negative, so let's suppose this bias is a very large negative number. Let's say it's negative 100. Then what are the chances that it's going to be greater, that the whole thing is going to be greater than 0? It's going to be small, right? So it's going to make it harder to be greater than 0, right? So it's going to make it harder to get an output of 1, right? So in other words, it's going to make it harder to fire. Right? We said the neuron's going to fire, right? So when the b is large negative, when the b is a large negative number, the neuron is not likely to fire. It's going to take a lot of input to make it fire. Okay? On the other hand, if the b is small, then it won't be so hard to fire. Okay, or to put it in more biological terms, the bias is a measure of how easy it is to get the perceptron to fire. Right? So if it's large, negative, it's not easy. If it's positive or small, it's easier. Any questions so far? Okay, let's take a short break, because that was kind of intense. And then we'll come to sigmoid neurons instead of perceptrons. And the difference is this, let me warn you beforehand, the difference is going to be that when we get an input into here, we're going to pass it through a function. We're going to put that input into a function. And then we're going to output that function. Okay, and the function we're going to use is which function? Sigmoid function. Okay, that's going to be the, so we're going to take the same input that we were just working with, but we're going to put it into the sigmoid function. So that's going to, and by the way, the sigmoid function always gives us a value between what and what? What's the lowest possible value? 0, and the highest possible value is 1. So even if we get a huge number for x, right? We're still going to put it into the sigmoid, so the biggest number we're going to get out is what? 1, and the smallest number is 0. Okay? So that's what we're going to do next. Well, let's take a 5-minute break, and you can go outside or whatever you want to do.